Hello everyone, welcome again to this video. In this video we will be discussing about another special integral. So let me name the integral. So let me just show you what we are going to do in this session first. We are going to evaluate this is the integral that we are trying to evaluate, and we have to evaluate it in terms of elementary functions. Remember that. Okay, so again, just a notice, this is not an integral where you try and you can try your elementary methods or methods that you have learned so far, but it's rather an integral where we have to be very much creative. Okay, so yes, you know the stuff that needs to be applied, not really from integration, but well, you need to know all of the integration as well, but you do need to know some other stuff such as Maclaurin series and stuff like that, how to find a Taylor series of a function. I actually have told you all of that when we were covering the derivative section, and you will see how much interrelated this is once we try to get to the bottom of this integral. Okay, so denote the integral by I. Now I should be equal to 0 to 1 ln of 1 minus x by x dx. Right. So this is our I, and we wish to find this. Well, first of all, what we are trying to do here is we are going to apply the following property. So a to b f of x dx would be equal to a to b f of a plus b minus x dx, right? So this is basically the property that we are going to apply, and to apply this we see that I is equal to 0 to 1 ln of 1 minus x by x dx, and you can see a is 0 here, b is 1 here, so a plus b is basically 1, and replacing x by a plus b minus x here is meaning replacing x by 1 minus x, right? So you have to replace all the x's by 1 minus x. That is what the property tells us to do. So when we do that, we see this x becomes 1 minus x and this x becomes 1 minus x, right? So when we simplify, the result is something like this: log of x by 1 minus x dx. So it seems that the 1 minus x and x just have interchange places, but this is a real benefit to us, and in the other solution to this video I will show you how to do this problem without using this property. So there are two ways to do, more than two basically, but I'm going to show you two of them, both of them interesting enough. So for this one, we have the following integral, which is 0 to 1 log of 1 minus x by x dx, which was transformed into 0 to 1 log of x by 1 minus x dx, right? Now notice that 0 less than x less than 1 also implies mod x less than 1, right? And therefore 1 by 1 minus x is basically equals to 1 plus x square plus x cube and all the way up to infinity, which is the geometric series, which is only valid when mod x less than 1 is valid, and in this integration region 0 to 1, it directly implies that mod x less than 1 is also true. So this can be written as n equals to 0 to infinity x to the power n. Okay. So therefore I equals to 0 to 1 ln of x into 1 by 1 minus x dx, and obviously we change it to ln of x into summation of n equals to 0 to infinity x to the power n dx, right? And once we do that, what happens is we can take this summation outside of the integral using a lot of known theorems, one of them being the dominated convergence theorem and Fubini's theorem. So we can prove that we can swap the integration and the summation sign, and it is valid here. And when we do so, what we get is n equals to 0 to infinity 0 to 1 x to the power n into ln of x dx, right? Right. So now what it comes down is to evaluate this following integral, which also can be evaluated in two ways. I can see two ways to evaluate this. So let me show you at least one right now. So let t equals to 0 to 1 x to the power n into ln x dx. In our Eilert rule, we know that algebraic and logarithmic comes first and algebraic comes second. So let us do that. So logarithmic is first and algebraic is second. We have ln of x into integral of x to the power n is x to the power n plus 1 by n plus 1, and we go it from 1 to 0, 0 to 1 basically, minus 0 to 1. Differentiation of log x is 1 by x, integration is x to the power n plus 1 by n plus 1 dx. As you know, log of 1 is 0, so first part is 0, and then if we put in 0, log of 0 is minus infinity, but then x to the power n is also 0. So basically using the L'Hopital's rule, it can be proved that this is also 0, and what we are left with is something like this: minus 1 by n plus 1 0 to 1 x to the power n dx, and again this evaluates to minus 1 by n plus 1 x to the power n plus 1 by n plus 1 from 0 to 1, which is again 1 by n plus 1, which means it is minus 1 by n plus 1 whole squared. So therefore, putting this value, we get, therefore I is equals to minus summation of n equals to 0 to infinity 1 by n plus 1 whole squared, or we can write this as minus n equals to 1 to infinity 1 by n square, right? Now, what is this series? This is one of the most beautiful series in mathematics and one of the oldest problems basically. So this series basically, just ignore the negative sign for now. We just want the value of this series. It just says you it's 1 by 1 square plus 1 by 2 square plus 1 by 3 square and all the way up to infinity. So this is called the Bessel's problem. This is called the Bessel's problem, and it was attempted by Leonhard Euler back in 1764, and he did solve it, right? And in doing so, he had made a factorization of the element sin x, and what he did was he guessed what was the front function. What he did guess was came out to be correct and was proved later by Gauss that it was indeed correct, but the value he provided to this series, that is the sum of the squares of the reciprocals of the natural numbers, was pi squared by 6. So it only makes sense that when you have a bunch of rational numbers, that is 1 by 1, 1 by 4, 1 by 9, and you add all of the rational numbers, what you get is a rational number, right? But consider the fact that there are infinitely many of them, that is, you're never going to end. So you're only going to reach some limit, and remember that pi itself, even if it is a constant, it's the limit itself. So when we are actually expressing the sum of infinitely many rationals as an irrational number, it makes sense because the irrational number also has a limiting value, right? And this rational numbers also have a limiting value, so maybe both of them correspond to the same limit, right? So anyways, the proof of this series will be provided in the next video, which might be actually a very big one, but I will try to prove it and let it go there. But just understand for this fact, this is also called the Riemann zeta function. This is also called the Riemann zeta function. Okay, and Riemann zeta function is denoted as zeta of s by 1 by 1 to the power s by 1 by 2 to the power s plus 1 by 3 to the power s and so on. And this specific value is zeta of 2, which is pi square by 6. So anyways, we will discuss more in the next lecture. For now, this should be the end. I hope you have liked the video and the new topics that I'm bringing to you. So for future lessons, keep on tuned, and also do download the Breatter Math app, which the link is in the description of the video, and you can download it. You can see all the related video solutions, this video and its related theory, all of that in that app. And you also have bunch of statistical calculators and probabilistic calculators where you can do derivative integration, find probabilities and stuff. So do check it out, and thank you for watching.